So ACI defines the tension controlled and compression controlled sections as the ones, as we said, the ones that are compression is dominating, which means the concrete crushes before tensile steel is yielded as compression controlled section. And then it talks about the tension controlled. Now we're not talking theoretically, we're talking practically now. Now if I want to define a section as pure tension controlled, it is not only that I have yielded first the steel, but also I want to make sure that the steel has reached 0.005 strain at yielding. Let's get back to this. We understood that during the time your section is failing, if both of those guys happen together, imagine that compression got to a strain equals to 0.003 in concrete, and steel have yielded exactly at the same time. This is balance point. So that means the strain in the steel, which is a tension strain, equals to what? 0.0021, right? And we said this came from Hooke's law for an F yield equals 420 and epsilon megapascal, and a modulus of elasticity equals 200 gigapascal. Using Hooke's law, we will get a strain equals 0.002 as yield strain. So that means anytime your yield strain is bigger than this at failure, you're theoretically in a tension controlled zone. But this is not what the code is telling you. The code is telling you you will not consider it as tension control unless this value is equal to 0.005, which means I would like that the section to be a tension controlled section to actually be somewhere here. From here on, it's tension control, where this value equals to 0.005. But hold on, what we talked about is that if it yields first, which means if it reaches 0.0021, it's already in tension control. The code tells you no. For that part, we will call it a transition period, a transition zone. This is a region that is actually a whole region between compression control, going this way will be compression controlled, going this way will be tension controlled. And what's here in the middle is the transition. Okay? Why do we need to know about this? Is because of the phi factor. So in the zone of compression control, my phi factor will be equal to 0.65. In the zone of the tension controlled, it will be the phi factor equals 0.9. And then in the middle, it will be somewhere in between the two numbers. Okay? So again, theoretically speaking, you are in tension control within the transition region, but practically speaking, we don't consider it as tension control. Now, compatibility of strains tells you that you have two similar triangles. This is the first triangle, this is the second one. Or in other ways, we can consider these two triangles. So you have this big green triangle and this little small triangle, right? So in this case, if I say C over 0.003 or C over dt equals to 0.003 over 0.003 plus epsilon t. Okay? So the whole triangle, or the two triangles, the two similar triangles, gives me this relationship. Remember when we said that it's important to use compatibility of strains, which is the fact that that line is a straight line. Okay? If that was not straight line, I will not be able to do this relationship. Now, for a tension controlled section, you will substitute this guy with a 0.005. Now that 0.005 or more, that gives me tension control. So in this case, my C over dt, this ratio, if it's more than 3 over 8, then it's tension control. So when I want to know do I have a tension control section or not? I just simply check my C over dt. If it is 3 over 8 or more, I am in a tension controlled zone. Now, set by the old version of the code, the old version of the ACI code, which is 2011, they used to have a provision for maximum amount of steel at failure, if you have the chance, to have a nominal strength at a maximum, at a minimum tensile strain in steel equals to 0.004. So they used to set this up to specify the maximum amount of steel, which means do not increase your steel above this limit so that you're always in a tension control zone. Now this provision was removed from the new code, but I just placed it here because in the tables you will see a column for the 0.004. This is where it came from. Now those are three parts of, or three types of failures. Compression control is this or less. Tension controlled is this or more, right? And in between here, I have what I called a transition zone. And then within the transition zone is the old code provision for the 0.004 being the minimum tensile strain in flexural members. Now the code also tells you that if you don't need much of steel, if your design, so for example, I have a really big section, but I have very small moment, right? So MU was very small. Now, can I freely put any type of little amount of steel here? The answer is no. You have something called the minimum amount of steel, AS minimum. So if by your design you required less than AS minimum, you will have to take AS minimum as your limit. What is AS minimum? It's the bigger of these two values. 0.25 square root of F prime C over F yield B times D, or 1.4 BD over F yield. Which means if I want to specify my rho minimum, I simply remove the BD. Why? Because rho equals area of steel over BD. Okay? Very important. Now, rho is the steel ratio. Which steel? Only the tension side steel. I don't put the compression side steel as well. Okay? So in case my AS that was required is larger than AS minimum, I'm good. If AS is smaller than or less than or equal to AS minimum, then I use AS minimum. Okay? That's a basic requirement. Now, is there an AS maximum? There used to be an AS maximum. Is there a rho maximum? There used to be. In the old code, rho maximum was there, which is the rho 0.004. Now it is removed and you're not required to do it. In other words, the ACI code allows for compression controlled design sections. This is the provision of the code that talks about AS minimum for your reference. This is the removed design limit for AS maximum that we will not use. We used to call it rho of 0.004. Again, I'm putting it here so when you see it in the tables, you would understand why it's there. Am I required to do it? You're not required to do it. Let's now understand how we do the analysis. Said that the given is the material properties, the cross-sectional dimensions, the steel area, AS, and the loading conditions, which gives you M, or allows you to calculate MU. And now what you will find is the D, DT, FS, phi, and then calculate phi MN and MU and compare them together to check your adequacy. Now, as we said that the sigma forces equals 0, that means C equals T, and AS equals 0.85 F prime C AB. This guy is the T, and this guy is the C. And then from that, we can estimate our A to be equal to FS, ASFS over 0.85 F prime CB. Now I was able to get A, and A is very important to find because it is part of calculating my moment. Why? Because my moment equals any of these two, c or t, times the distance, which is d minus a over 2. Okay. And then the next step is to just calculate mn, and in this case, mn equals to any of them times the distance. So we can substitute with any of them times the distance. And then calculate phi and multiply mn by phi. That gives me my design moment strength. So this here is called the design flexural or moment strength. Okay? So design moment strength equals to phi times the nominal moment strength. Getting into the most critical part. Now, I don't know what Fs equals to. Fs is the stress in the steel bars, right? Now, the steel bars, if they are yielded, then Fs equals F yield. If they're not yielded, then I have to use Hooke's law along with compatibility of strain. So simply within my design, one of the important steps to do is to calculate the balance amount of steel. So rho balance. Where did this equation come from? It simply came from putting together 0.003 up on top and 0.0021 down at the bottom. And then they calculated how much amount of steel is needed to attain this condition. Now that amount of steel, or this rho, this ratio, is a value that I will compare my rho to. So I'm comparing rho, which is my AS over BD. My AS over BD. I compare it to rho balance. I just calculate rho balance and then find which one is larger. Now if I was less than rho balance, that means I have yielded my steel and my Fs equals F yield. Very simple. It is a more preferable solution. I always try to do this in my design. I try to use the steel that I have at failure to have the yielding condition. Now, if it is more than rho balance, what happens? I don't know Fs. Then I have to solve two equations in two unknowns. What are those two equations? It is C equals T and C over dt equals 0.003 over 0.003 plus epsilon T. This came from compatibility of strains. This came from force equilibrium. Now, the two unknowns here are the C and the epsilon T. I know everything else. I know F prime C, beta 1, and B. I know area steel, and I know my modulus of elasticity of the steel. Now, going to the other side, I'll see that I know only dt, and I'm missing those two. So those are two equations and two unknowns. I solve the two equations, and I find C and epsilon T. Now, from C, I'll be able to find A, because A equals beta 1 C. And from epsilon T, I'll find Fs, which is this. So I can simply solve them by using two equations in two unknowns. Now, this is the ACI curve that shows what are the phi factors compared to different failure conditions. So I have a failure condition that is compression controlled. I'm going into the 0.65. Tension controlled, I'm getting into the 0.9. It's very high. And then in the middle, I have a straight line relationship. Now for columns, we will have something called the spiral columns. It doesn't go down to 0.65, it goes down to 0.75. And then in the middle, I have phi having this equation in terms of epsilon T. So in this case, we have two ways to look at the phi factor. The first way is by comparing C over dt to these values, or comparing the tension strain to these values. It will give exactly the same. And we just knew how 0.005 was able to get a 3 over 8. So it is equivalent. If you're solving a problem, you can use either or. It will give the same exact answers. So it's 0.9 to to 0.65, and in between we use this equation, or in between we use this equation. Controlling the flexural cracks is one of the problems that if you get your bars very far away from each other, so you've had bars that are really at big distance, you will end up having big areas without rebars, and that may cause some wider cracks than anticipated. So in this case, we make sure that the distance S, which is center to center, we call this S, is always bigger than, is always smaller than S maximum, or sometimes we call it S allowable. Okay? This is just to control the cracking for having distances or large distances between cracks. How do we do this? Is based on the code equation. We have two equations. Those are the two equations from the code. We take the lesser of them to be the maximum spacing. Okay, so the maximum spacing, S max, is the lesser of these two values. What are those two values? They contain, here, maybe it's not very clear, is 380 times 280 divided by Fs minus 2.5 cc. Now, or the other one is 300 times 280 over Fs. Now remember, in these two equations, Fs is not the actual steel strain or stress at failure. We are controlling this at service load. So at service load, they said you're allowed to take Fs only for this calculation, only for these two. You're allowed to take Fs equals 2/3 of F yield. Simple. So when you get to calculating the S max, your Fs is not the Fs you used in the nominal mode because you're at service load. So in this case, take it as 2/3 of F yield. And then what is Cc? Cc is the clear distance or the concrete cover to the bar. So remember that we used to take the cover to the stirrups. Here are the stirrups. And here's my bar. In the old days, I used to say that this is my clear cover. Now, for purposes of calculating S, this will be my Cc. That's why it's actually C sub C. Okay? So it will be the 40 plus 9.5. Okay? So in calculating S max, I'm not using the clear cover given to me to the stirrups. I'm using the clear cover all the way to the bar. Okay? Getting into the summary of calculating or and analyzing rectangular beams, compute the clear spacing and compare it to clear spacing minimum. I would suggest that also having an S compared to S max is another good practice. And by more practice, you will start looking at tables and just comparing things on the table, which makes life much easier and much faster. Compute the row and row minimum. Compare row to row minimum. If it's okay, go ahead. If not, then increase reinforcement to use at least AS minimum. Compare your row to row balanced. Why do I need to do this? To check what the value of Fs is. It is preferred to have row less than row balanced, so your Fs equals F yield right away. Compute your A. In this case, in case it's equal to Fs, then you substitute with an F yield if it's yielded. If not, then you have to do the two equations, solution of two unknowns in two equations, and then calculate your Mn by either using the T or the C equation. And then we calculated the C dt over C or C over dt, and then phi multiplied by Mn, and then compare it to Mu. Very simple steps that you will have to go over in your design. Let's take example 1. Consider the rectangular cross-section shown of a singly reinforced beam under positive bending moment, the concrete compressive strength F prime C is 35 and megapascal, and the steel yields at 400 megapascal. Now we have a cross section here that has two layers, which means your d and dt will be different. By considering the most congested layer, is the criterion for minimum clear spacing between parallel bars satisfied or not? We're checking now CS versus CS minimum. The equation for CS minimum is the larger of dB and 25. That's because I don't have the aggregate size. So I just skip the aggregate size check. Now what controls is 28.7 compared to CS. Calculating CS is simply, we're calculating this distance. So I have to take the whole width minus the covers, minus the stirrups, minus the bars divided by 2. And then that gives me 32. Now that was bigger than the minimum. It goes to 28.7. Then it's okay. Now, can I use the tables instead of this? Yes, and we will check those tables next chapter because that saves us a lot of time. The next step is to find the distances d and dt. Simply d, or dt is the distance all the way to the last layer, and d is the distance dt minus the distance all the way to the centroid of the bars. In other words, I have my bars, I have 3 bars down here, and I have 2 bars here. This here becomes my dt, while this here becomes my d, to the centroid of everything. Okay, so that's what I'm looking at. What's the tensile steel ratio? Rho equals AS over BD. Now I calculated my D, simply multiplied by B and divide your area steel by that multiplication to give you 0.02. Comparing rho to rho minimum to check on the provision for minimum amount of steel, I calculate my rho minimum. My rho minimum equals 0.0037 or 0.0035. So we take the bigger of them, which is this one, compare the number I just got for rho to rho minimum. It's bigger than the provision is satisfied. If it was not bigger, then I take AS minimum or rho minimum in my account. What's the value of the stress Fs? How do I know the value of Fs at nominal strength at failure? I simply compare my rho to my rho balance. So I have to calculate my rho balance, which has this equation. If my rho was less than rho balance, that means I've yielded the steel, and Fs equals F yield. Then finally calculating Mn. What's Mn? I have to calculate A, or the equation of ASF yield over 0.85 F prime CB. I got 173.45. My Mn is equal to that tension T times the distance G minus A over 2. That gave me 544 times 10 to the 6 Newton millimeters. Divide this by 1 million to get you in kilonewton meter. And then the design moment strength, that means I multiply it by phi. How do I get phi? I need to know if it's tension controlled or not. So I calculate C over dt or epsilon t, any of them, and then compare the numbers. I will find that epsilon t was less than 0.005. That means it was in the transition period. Transition region. That means phi is between what two values? 0.65 and 0.9. So now we calculated it, it ended up being 0.85. Then phi mn, I simply multiply this number by 0.85 to give me this number, 462.5. The next example tells you that for the same beam that we just calculated, what is the maximum load? We're trying to get the maximum concentrated dead service load that can be placed at mid-span. We're trying to place some load at the mid-span, assuming that only the distributed load is coming from the beam's own weight. So in this case, automatically I will know that it's only dead. And then the governing load combination for me is 1.4 dead. So before even I start, from the givens, I can say that 1.4 dead will be used. So in this case, I will convert this into ultimate by multiplying the own weight by 1.4. Here's the own weight. It's 0.25 times 0.6 times 24 kilonewton per square meter, or cubic meter, which is gamma concrete, times the 1.4, that gives 5.04 kilonewton per meter. Now, looking at the load itself, I have the moment coming from two different places. Moment coming from distributed load and moment coming from concentrated load. So the maximum moment here will be equal to the summation of these two moments. I have two moments, WL squared over 8 and PL over 4. So that's what I have here, PL over 4 and WL squared over 8. I have the W from the own weight I just calculated, but I don't have the dead load of the concentrated load. So I will substitute with 1.4 QD. What's QD? It's this guy. Okay? And then I will say that this here, which misses the QD, will be equal to my maximum moment that can be applied. What's the maximum moment? Phi Mn. So I basically equated the ultimate moment with the design strength. And then I got 209 as a concentrated load that can be placed. Can I increase this and say, for example, 210? The answer is no. If you're looking for a load as the maximum load, this is the maximum you can get. If I round this, I will have to round it down. So I can say 209, 205 as a way of rounding, not to round it up. What is epsilon S over epsilon yield at nominal strength? I have epsilon S from this equation, gives me 0.004. Epsilon yield is 0.002, or 0.002 comes from this F yield. Then the ratio is 2, which means I'm at twice the yield. I'm here at twice the yield at failure. My epsilon S is twice epsilon yield. And in this case, I can say this is why we used Fs as F yield. Example 2, a reinforced concrete cantilever of span equals 3.5 is subjected to uniformly distributed dead load in addition to its own weight equals to 9.5 kilonewton per meter, and a uniformly distributed life load equals to 10 kilonewton per meter. So that means I have here W dead plus W life. That's 9.5, and this here is 10. In addition to the cross-section of the beam itself, it's fixed to a wall. F prime C equals 25, F yield equals 300, and concrete is normal weight. This is how the section looks like. As the beam is singly reinforced, is the criterion for minimum clear spacing satisfied or not? Then we calculate CS minimum and CS, the same steps as we did. CS is simply this distance. And CS minimum, since I don't have the aggregate size, it will be the bigger of GB and 25. Now it is satisfied, then you're okay. Your next step is find the distances between D and DT. Since it's one row, that means D equals DT. So I just say 500 minus the cover minus the stirrups minus half of the bar. That gives 432.6 millimeters. The tensile steel ratio comes from AS over BD. then it's equal to 0.02. Is the provision for minimum amount of steel satisfied or not? Then you calculate row minimum and compare row to row minimum. Looks like row was larger than row minimum, then provisions is satisfied. What is the value of Fs at nominal strength? I simply calculate row to row balance. So I calculated row balance based on getting beta 1. I got row balanced equal to 0.04. My row is less than row balance, then my Fs equals F yield. That means my steel have yielded. What's the value of the nominal strength? If I say nominal moment strength, that's Mn. If I say design moment strength, that's phi Mn. And in this case, I calculate A. From A, I plug it in the equation. I know that Fs equals F yield. And then I found Mn divided by 1 million to convert it from Newton millimeters to kilonewton meters. What is the value of the design moment strength? Now I need to calculate phi, and to calculate phi I need to calculate either epsilon t, the strain and the tension, or C over dt and use either of the two. In this case we calculated epsilon t from the equation. We got epsilon t equals 0.004. That's less than 0.005. That means it's in the transition region. So that means phi is between 0.9 and 0.65. And in this case, we use the equation for the transition region, and phi Mn equals 287.5. Is the design for Flexural adequate? Is it enough? Is it safe? Yes or no? We have to calculate Mu. And to calculate Mu, I have to calculate ultimate load from W dead and W life, which were given. But W dead will be the two loads together, the 9.5 in addition to the own weight. So the own weight ended up being 3.6. 3.6 and 9.5 is 13.1, and the life is 10. And in this case, I'm not using the 1.4 dead, I'm using the 1.2 dead plus 1.6 life, because I have a significant life load which will make this load combination governs. So in this case I have an ultimate load equals 31.71. I need to calculate the moment at the maximum location, which will be here. So Mu max will probably be at the face. Then you calculate WL squared over 2, because this is a cantilever. That gives 194.7. Compare it to phi Mn, it gives you the answer that the flexural design is adequate. Now, in addition to this, what if I want to add a load at the end? Now, here is the load. I want to add a machine or something like it's a life load to the tip of this cantilever. What's the maximum load I can add? Simply, I was told that I have a 194 moment, but the capacity is 287. So the difference is what I can add. The actual added moment, M added, can be estimated from the difference between these two moments, the applied and the capacity. And then I divided by the length to get the load, and then from the load I reduce the ultimate to service. So I divided by 1.6 to become 16.6 instead of 26.51, which means the maximum additional concentrated life load that can be added at the cantilever tip is 16.6 kilonewton, or 1692 kilogram force. These questions are very common, especially for retrofitting purposes and adding weights to existing structures, that you can calculate the capacity and see how much load can be added within the safe region of the section.